1, 2, 3.
Take me out to the ball game, take me out to the crowd. Buy me some peanuts and Cracker Jack. I don't care if I never get back. Let me root for the home team. If they don't win, it's a shame. 'Cause it's 1, 2, 3 strikes, you're out at the old ball game.
Special verse for AABC.
Take me out to the tap show, out to AABC. Teach me some tap tips for hospitals, but only virtually. 'Cause it's test patient rooms now. Isolate COVID-19. Tap is fast, faster, easier now. Thanks to Evergreen. Bye, ASHRAE Show.
Great show.
Good afternoon, everyone. Robin's just getting his presentation ready. I'd like to welcome everyone to day 5 of AABC's virtual annual meeting webinar series. I'm Sam Schwartz, and I'm Member Engagement and Marketing Manager for AABC. Welcome, everyone, once again, and thanks to Evergreen Telemetry for their support. Love that video. I am just going to go over a few Zoom notes while Robin gets his presentation up. If you have questions for our speakers, please use the Q&A button in your Zoom window and not the chat box. We will feed those questions to our speakers at the conclusion of the presentation and to answer as time permits. You can also submit questions at any time, so there's no need to wait until the end of the presentation to do so. If you have technical issues, please use the chat box for that, and our technical specialist will assist you. Today's presentation is effects of temperature change on building static pressure measurement with our presenter, Robin Rader of Design Alaska. Robin is a certified professional engineer and a certified commissioning authority through ACG. So without stealing any more time today, I'm going to hand it off to Robin to kick us off. Robin? And Robin, I believe you're on mute there, so if you just unmute yourself.
There we go.
There we go.
Okay. Hope everybody can see my screen. Yeah, we will take it from here. It was 24 below this morning in Fairbanks, Alaska, so we are entering a nice cold winter. All right. So for static pressure sensors, there is an error induced in the tubing when the height of the outside reference point is different than the height of the indoor reference point. In this case, the error is driven by the outside pressure difference, or the difference between the outside air and the inside air due to stack effect. And it depends on the height difference and the temperature difference of the outside air, and it can be as significant as 4 times the control point. I'm going to talk a little bit about static pressures within a building. Negative pressure within a building is a bad deal. It shoots drafts into all the wrong places. Clients or receptionists, security guards are all subject to harsh temperature swings. Some various pressure levels, 1/10 of an inch is the upper boundary where an automatic door closer can function. Elevator doors start to have trouble beyond a 1/10 of an inch, things like that. At a 1/20th of an inch static pressure, manual operation of a standard 3/0 door is physically difficult, requiring 2 hands on the knob to pull it closed or a shoulder to push it open. The 0.05 inch water gauge pressure is the industry standard control point for building static pressure. At that pressure, automatic doors function acceptably. Some commissioning agents are setting building static pressure now at 0.03 inches water gauge, which is feasible because of the increased accuracy of our differential pressure sensors. Just for reference, 0.01 inch water gauge is the minimum control point allowed for sterile room boundaries. These include formularies, sterile processing, that sort of thing. So building stack effect. So stack effect happens on a building just to keep the structure warm. So the difference between 70 degrees inside and minus air temperatures puts a stack effect on a building. So from ASHRAE fundamentals, you can see that a building with a roof height of 75 feet with an interior temperature of 70 degrees and an outside temperature of minus 40, the internal static pressure varies nearly 3/10 of an inch, with the static pressure at the roof elevation at a positive 0.15 and at the ground floor at a negative 0.15. This relationship can be shifted by drawing in excess incoming outside air compared to exhaust air or exfiltration. The necessary amount of excess air depends on the tightness of the building. So to achieve 0.05 inches positive pressure at grade, in this example, the pressure at the roof would have to be increased to 0.35. So the relationship between static pressure and infiltration and exfiltration is similar to Ohm's law, where voltage equals current times resistance. In this case, the voltage is the same as the stack effect. The resistance is the tightness of the envelope, and the current is the amount of infiltration or exfiltration. So the tighter the building, the greater the R, the less unwanted infiltration and exfiltration. Note that V increases with building height for a given temperature difference between the inside and outside. So in Alaska, my home state, there are no high-rise buildings north of Anchorage, at least based on the building code designation. Cities like Edmonton, Calgary, Chicago, and Minneapolis contain buildings with the greatest stack effect potential. However, in Fairbanks, there are extended periods of cold weather with low average temperatures for months at a time. So that's far too long to not address the problems caused by stack effect. Maintaining positive pressure on the ground floor of tall buildings in cold climates is impossible. At least that's the conclusion we've come to. The interior area must be designed to account for significant infiltration. So you see people doing things like putting saran wrap over the sprinkler or the roof drains and things like that. So at cold temperatures, trying to maintain positive pressure in buildings is very difficult. So this building here is the building where our company became aware of the issues with the static pressure being offset by the tubing height. So this building is 75 foot high. It is just below the high-rise designation. If you can see my mouse, I'm surrounding this entry area. This is a 2-story entry area. So this was a great challenge for us to try and make the environment inside this area a tenable environment. So I'm going to talk about Arctic entries a little bit. A typical Arctic entry has 2 sets of doors, and they have adequate travel distance between the doors so that typically one set of doors is always closed. So when you calculate the heat required for this entryway, the way you do it is you multiply 3 times the square footage of the door panels. So in this case, you got 2 doors, and so that's about well, anyway, so you calculate the CFM is 3 times the area of the doors times 0.08 times the design delta T. So when you get that number, you should put 1/3 of that heating requirement in the vestibule itself, and you should put 2/3 of that heating requirement just outside the vestibule. So the 1/3 will keep the sprinkler head from freezing. It'll keep the floor reasonably warm. And so this will be a tenable environment within the entryway itself. The cabinet unit heater outside the vestibule picks up the cold air that gets through as people pass through this entry. So this is a picture of the of a cabinet unit heater used for entry heating. Note that you pull air into the bottom of the cabinet unit heater and blow it out the top. This sucks the cold air through and warms it. And so this unit heater should have a high flow, should have like a single row coil so that you get a high flow and relatively low delta T out the cabinet unit heater. This is a ceiling cabinet unit heater. These don't work well. They do keep the sprinkler head from freezing, but that is about it. They can't warm any occupants. The heat stays on the ceiling, and it's just a poor way to do it. However, if you are not running glycol in your heating system, you're forced to use a cabinet unit heater in this configuration. Otherwise, you'll freeze the coil. So this is a picture of an air curtain. It's somewhat similar to that cabinet unit heater. Our experience in Fairbanks with air curtains is bad. Typically, the air pressure is negative enough that it pulls this stream off of the door and allows cold air to flow in. This hot air that is blown down essentially is turned up and goes to the ceiling, and so the occupants don't feel any effect of the hot air from this air curtain. So ASHRAE has now allowed single doors with an air curtain, and I'd be very careful with this. I certainly wouldn't use it where there's any occupants that are near the entry. Okay, so here's another couple entries. Entry on the left is split. so that incoming traffic is segregated from outgoing traffic. And this allows the doors to be closed more often. And so that's if you can make that happen, that is a good thing with an Arctic entry. We've done this in a lot of our medical facilities up here. This is a picture of a revolving door, and we don't have any revolving doors in Fairbanks currently. The ones that have been here have been taken out, and I'm not sure why. I know that they work. I've seen them work in Calgary, but I think the doors up here possibly have frozen down to the floor. At any rate, none of the owners in Fairbanks use revolving doors anymore. So this is a picture of a entry configuration that didn't work. Even though we have split entries and exits, we have a cabinet unit heater on each side of this entry. We didn't put a cabinet unit heater just outside. And so what happens is any cold air that comes out this entry gets pulled along the floor all the way to this piece of fin tube. And so we got seats here for all the occupants, and they are subject to this cold air. Now you'll notice that we did do something correct as far as the receptionists. They have a fully closed area, and so their counter is say 4 foot high, and that protects them from cold air. And so our receptionists are fully protected from the cold air, but the people waiting in the occupant area are not, and this was a problem. Okay, so I'm just going to recap building entry design real quick. Vestibules with 2 sets of doors and reasonable travel distance. Split the vestibule, separating incoming and outgoing travel flow, decreasing the potential of both doors open simultaneously. Radiant heating to prevent automatic doors from freezing to the floor due to ice buildup. So if you've got a new facility and you're going to put in electronic doors on the outside, get radiant heat into that vestibule. You'll still need a cabinet unit heater. Radiant heating doesn't have a high enough heating density to heat the space all by itself, but it will keep that track from freezing. Weight heating capacity towards the occupied side. Assume cold air escapes the vestibule. Wall mount cabinet unit heaters. If you do though, you've got to protect them with glycol. For high stratification lobbies, that is lobbies with high ceilings, draw the air into a heater as low as possible. Select the heater with high flow, low delta T configuration. Under cold conditions, that is -20, switch control modes to run the cabinet unit heater fan continuously and modulate the coil flow to maintain temperature set point. So on important vestibules, put a modulating control valve on the coil and switch control modes when it gets cold. Work with the architect to provide wing walls to protect lobby seating areas or receptionists from cold air racing along the floor. One thing that we did at the Rabinowitz Courthouse is we closed off all the return air openings out of the entry, this 2-story entry area during cold weather operation. And this was the final, this was done a couple years after the building was occupied. It was the final thing that we did for this entry, and it helped significantly. So we pressurized this, the whole entry area, and made a huge difference. Okay, so now we're going to talk about accurate sensing of building static pressure. So static pressure sensors are subject to wind and temperature difference. So we're going to talk about attenuating the wind effects. So here's a picture of a building with wind blowing from the right to the left. And so we have a high pressure side on the right. The wind pressure envelope goes over the building and off to the left. And so here is a outdoor reference, and this reference is subject to wind pressure, which can go many times over the control point. Here is another outside reference that is above the building, and it uses a wind attenuating head, which consists of two plates with a little opening in the bottom of the bottom plate. And so then the airflow is orthogonal to this sensing point, and the wind doesn't affect that point. And so you want these things as high as possible. I drew a line here underneath this thing as far as where the pressure envelope goes, but it's hard to tell where that pressure envelope is. So the higher these things are above the roof, the better. This is a picture of another outdoor reference. And so one thing that can be done is you can average the one sensor on one side of the building with another sensor on the other side. However, during wind, the two pressure relationships don't actually equal each other. And so your average is not, doesn't really fit exactly. This is just a plan view of two pressure averaging system. Different equations for the same phenomena. So I'm going to talk about equations you can use to get an accurate sensing condition, even if you have your sensors at two different elevations. So this equation below is the buoyancy equation that you can find in ASHRAE, and it can show you what stack effects pressures you will have at different outside air temperatures. This equation here is called the hypsomatic equation, and it is an equation that meteorologists use. This is a table that pilots use to adjust their altimeters if they are flying from a warm area to a cold area or vice versa. So in this case, if you are flying from an area that was above 10 degrees to an area that was 40 below, then you would need to adjust your altimeter 240 feet for every 1,000 feet. So these three equations give different results. So, and I don't know which one's more accurate, to tell the truth. I chose we've chosen the buoyancy equation to calibrate the outside air. This is a graph of the offset due to height difference, and reading this, you can see that you can get up to about 2/10 of an inch difference if you set the zero of your building static pressure sensor at 68 degrees and it went down to 40 below. So that's the amount of offset that would happen if you had a approximately 50-foot difference in the elevation of your sensing tubes. This is just a different graph stating a similar thing. In this case, there's a fixed temperature difference, and it just shows what happens with the difference in height. So taller the building, the greater the difference. Got a picture here of a typical building pressure gauge. In this case, it can go negative to show you that you've got negative pressure, and then 0.05 is the typical set point. This is a picture of a standard building static pressure transducer. So you can also buy an auto zero transducer. An auto zero transducer can be set up so that it resets the 0 point every night. So this is a pretty inexpensive approach to this problem. It would work well with a wind attenuating reference point configuration. However, we don't use these things. I personally like to have a standard gauge next to the transducer that is reading the same thing that the transducer is reading. Whereas with auto zero, this would not happen because the transducer is being set with a new 0 point every day, and the Dwyer gauge would not be. Another thing about the auto zero transducer is it wouldn't work for systems that have to run 24 hours a day. So for instance, in hospitals, you've got no point where you can zero your transducer because you've got the difference between reliever and exhaust air versus the amount of incoming air, and you wouldn't know what that difference was. Also, well, I already spoke to that, so keep going here. So one thing that we've done in this case is we've used 2 transducers and 2 manometers in buildings. In this case, one of the transducer combinations is across the important door, say at 7 feet. So the outdoor reference is at 7-foot elevation, and the indoor reference doesn't have to be at this entry. It can be well within the building, is also at 7 feet. Then we also use a wind attenuating head at the top of the building. And so that transducer is the transducer that we control off of. And we run the sensor through this stack effect calculation to determine the static pressure. But when there is no wind, then we can look at the manometer across the door, and we can check our calculation and see where, what the actual building static pressure is. So this is an example of the algorithm that we put into the computer. We use English units just because I'm an old guy and I've learned English units, and I'm not comfortable with SI. The equation is a little bit simpler if you use SI because you don't have the gravitational constant in there, but other than that, this works fine. So I'm going to talk a little bit about transducer configurations and location considerations. So I personally like to have the transducers back in the mechanical room in a panel with the gauge mounted on the panel door. Controls people tend to like to have the transducer located by one of the reference points. So they'll on their, if left to their own devices, they'll put that transducer out in the ceiling space somewhere. So in my opinion, this is a bad idea. I want to have the transducers where I can get to it and I can calibrate the transducer and look at things. And I do this with duct static as well. I like to have the transducer in the mechanical room. The duct static pressure tube is long in that case, and the sensing of static pressure has a fairly large lag, but in my opinion, that's fine. And I don't see a problem with it. High duct static pressure sensors are different though. They need to act quickly. And so you need to have a short sensor in that case. Commissioning static pressure reference system. So a building static pressure reference system is a good candidate to be commissioned or checked. You can have problems with your reference tubing that are not readily apparent, such as broken or disconnected reference tubes that will report varying pressure information similar to what might be expected. And this can happen at different temperature regimes and things like that. So consider testing the building static pressure network tubing as part of the commissioning process. And this could be done simply by putting plugs at the end of the static pressure references. That way you get out there and you actually see where they put these references. So you put plugs into the ends of the static pressure, and then you blow the pneumatic tubing up and close off pressure and just see that it maintains pressure. So it's pretty easy to test. I took a picture of a baumometer. These are used by pneumatic control technicians if there are any around anymore. This would be something that you could blow that tubing up with, or you could bring a little air compressor or whatever. Okay, so I am ready for the conclusion of this this discussion. So why isn't the sky falling? Well, for many buildings, the static pressure under cold conditions is knowing that static pressure under cold conditions is not required for adequate building operation. So for many buildings, the outside air intake damper is set at minimum, and the relief air damper is set full closed at some outside air temperature determined by the building operator's experience, or this happens by the just by the control system. So your control system is trying to maintain building static pressure. It will drive this this relief damper closed, and you're at minimum, and that's it. There's nothing you can do to increase building static pressure. Now I'm going to talk about HRVs a little bit. So an HRV, you need to be a little careful with. Sometimes HRVs only will reclaim the exhaust out of a building, but sometimes they also reclaim relief air. And if that's the case, you may be relieving more air than you should be. So you need to take a hard look at that. I did a little calculation. So through the Corps of Engineers is starting to require building envelope leakage testing. I think the number they allow is 0.4 CFM per square foot. That's actually quite a bit of air, and buildings in Alaska are built tighter than that. A more tight criteria is 0.15 CFM per square foot. But anyway, you need to bring in enough outside air to blow against your building to maintain building static pressure. And if you're relieving air through your HRV, this might not be happening. And so you might have a negative building just on that basis. Now, as the building becomes larger or more sophisticated, accurate knowledge of building pressure becomes more important. It's of great importance if additional outside air is added to maintain building static pressure. This might be true in hospitals or other exotic facilities. Now, as far as a commissioning agent goes, though, accurate understanding of these issues is important to prevent you from being caught up in during the commissioning with unexplainable results. So you need to know the effect of cold air on building static pressure sensing tubing, and if it's causing you trouble, you need to address it. So that is my talk, and I will answer any questions.
Okay, thanks so much, Robin. So let's enter the Q&A portion. For those of you out there that still have lingering questions, please feel free to submit them to the Q&A button. We'll get us started here with the first question. Are there errors in BP measurement when DP device is kept in a panel and the outside pressure sensing tube is running over 100 feet away?
I don't think the horizontal length has any impact on the accuracy of the static pressure result. It does, the longer the tube, the greater the lag will be. But again, I don't think that's an issue. And 100 foot would not bother me a bit.
Next question, they're asking, what about the pressure drop through long runs of sensor tubing being greater than the static pressure you are trying to control to?
So pressure drop is a function of flow. And you actually have almost no flow even through 1/4 inch tubing. So I would not envision any pressure drop concerns through long tubing.
Okay, great. Robin, do you mind advancing the slide there?
Advancing the slide? Oh, not at all. Sorry.
Great, thank you. So next question. On your OSA averaging sensor, do you recommend an oversized pickup or tubing to help buffer the pressure?
No, we use 1/4 inch tubing. No, I don't think so. I don't think I would worry about trying to go to 3/8 or anything bigger.
Okay, next question. Have you seen separate absolute pressure measurements work successfully rather than physically connected indoor and outdoor sensors?
Could you repeat that question?
Sure. Have you seen absolute pressure measurements work successfully rather than physically connected indoor and outdoor sensors?
Boy, I'm not sure what that means actually. What an absolute pressure sensing might be. I wouldn't think so. I mean, I wouldn't think that even weather data would be adequate. I would think you'd have to compare your inside pressure to the outside pressure.
Okay, thank you. Next question, does the effective temperature change the static pressure of a building from positive to negative?
No, the reading is off-calibrated more positive as temperature falls.
How many times do I need to check sensors regularly?
Well, that's a good question. So in Fairbanks, we can get very significant temperature swings. It can be very cold, and then we can have a Chinook that comes through, and it can go well above freezing. So, we could have a 70-degree delta T, though that's rare that happens that way, but we could have a significant delta T in one day. So if you're not going to deal with the pressure change in your tubing system, boy, I'd say you'd want to check it daily. But yeah, that's a tough one. Yeah, I don't know really beyond that.
Okay. This next one is a two-part question. Do you think specifications should call out locations and installation standards for static pressure devices? And does your firm do this?
Yes, we do. We call out the location of the references, and we call out the location of the transducers and gauges. We call out the tubing and call for the tubing to either be run in a concealed space or in conduit.
What range pressure sensor is usually recommended?
I would try to get one. So the control point is 0.05, and some, you can get like minus 0.25 to plus 0.25. That is a good area for a building static pressure sensor. So you want to get it pretty low. You don't want anything up, say, in the 1 inch area. That's going to be awfully coarse and give you very little sensitivity.
Okay, thanks, Robin. If anyone has any lingering questions, please, now is the time to submit them. We have 2 more questions to get through. So next question we have lined up here. What about zoning the OSA intake from higher/lower floor systems, especially in the areas that you mentioned with high rises?
Say that one more time.
Mm-hmm. What about zoning the OSA intake from higher/lower floor systems? And then they wrote, especially in the areas that you mentioned with high rises.
Yes. So I've seen that in Calgary, where they had a outside air intake every 10 stories. And I think that is absolutely the best strategy for trying to mitigate a high stack effect. The elevators, unfortunately, will have to travel through these areas, and so you're still going to get stack effect happening in your elevators. Not sure how that's dealt with. I know down in Anchorage they've had problems with elevator doors not functioning during very cold temperatures. I'm not sure how they deal with that in cities like Edmonton and Calgary, but I would think they would have troubles with elevators that extend significant elevations.
Okay, last question we have in the lineup. Given your cold weather climate, seems that HRV and ERVs would be utilized extensively to bring OA in for energy efficiency and to maintain building pressurization. Do you run envelope pressure positive through this equipment to minimize infiltration? And if so, do you do this year-round?
So building static pressure is not a year-round issue. When it's warm, it really doesn't matter if you maintain a high building static or not. In my opinion, ERVs and HRVs can only effectively reclaim exhaust air. They are not particularly effective at reclaiming relief air because of the fact that you need so much outside air to pressurize your building. So a building with quite a bit of relief air is certainly a candidate for an HRV. Certainly a building that runs 24 hours a day is even a greater candidate for an HRV. I would say that ASHRAE pushes the requirement of HRVs a little too hard, and it's actually beyond economic recovery of the HRV in a lot of cases. Yeah, we use a lot of HRVs and ERVs in our area.
Okay, we did just get one last question come in. If we have different highest of building required to put more pressure sensors or only on the top of the building, is that enough?
Well, so your entry door is really where you want to measure static pressure. That's the area that you're going to get all your infiltration. And so putting your static pressure reference at the top of the building really insulates you from what's going on down at that lower entry door. So I would not recommend it. I'd push to get the your main entry door area as the reference point of your indoor reference at that elevation, I should say. So for instance, your building static pressure reference doesn't have to be at that entry. It just has to be at the elevation of that entry. So I think that answers that question.
Okay, thank you, Robin. That actually concludes our Q&A session. So thank you so much for giving us your time today.
Thank you.
For everyone that joined us, thank you again. We hope to see you tomorrow for hospital air balancing, planning, and coordination case studies. It starts at 1 p.m. Eastern tomorrow. And thanks again to our sponsor and AABC industry partner, Evergreen Telemetry. Stay safe and stay healthy, everyone, and see you soon.